In order for a reaction to occur, the reactant particles must collide with one another. Those collisions need to be in the correct orientation, and they need to have enough activation energy for the reaction to occur. The more collisions there are, the better the chance for successful collisions, and the faster the reaction will happen. The factors that affect the number of collisions, and therefore the reaction rate, are concentration, temperature, and surface area. A higher concentration of reactant particles means more collisions and a faster reaction rate. A higher temperature means the particles will move around faster and bump into each other more often, which means more collisions and a faster reaction rate. A greater surface area means more particles are exposed and able to bump into each other, which means more collisions and a faster reaction rate. Now it's important to note that with a higher temperature, more particles have enough energy to react, which is called activation energy, but we'll talk more about that later. And the last factor that affects the rate of a reaction are catalysts. Catalysts provide an alternative pathway with a lower activation energy so that more particles are able to react, but we'll talk more about that later as well. Transition state theory describes a hypothetical activated complex, or transition state, that occurs between the reactants and products, where the bonds of the reactants are breaking and the bonds of the products are forming at the same time. So in the example, the reactant bonds highlighted in yellow between oxygen and bromine are breaking at the same time that the product bond highlighted in green between the two bromines is forming. That hypothetical complex is called the transition state. The activation energy is defined as the minimum amount of energy required to break the bonds in the reactants and create that activated complex or transition state. So it's basically the minimum amount of energy that's needed for the reaction to occur. So let's go over potential energy diagrams. Potential energy is on the y-axis, and the diagram starts with the reactants on the left and ends with the products on the right. At the beginning of the reaction, energy is absorbed and used to break apart the bonds in the reactants. The amount of energy required to break apart those reactant bonds is the activation energy, or EA. Energy is then released when the bonds in the products are formed. If the reaction were to be reversed, the amount of energy required to break apart those bonds would be the reverse activation energy, or EA reverse. The top of the diagram is where the hypothetical activated complex, or transition state, occurs. That's where the bonds of the reactants are breaking and the bonds of the products are forming at the same time. Notice that in this potential energy diagram, the energy of the reactants starts out lower, and the energy of the products ends up higher, indicating an overall increase in energy during the reaction. When energy is absorbed during a reaction, delta H is positive, and the reaction is endothermic. Now let's talk about a potential energy diagram that looks a little different. In this diagram, the energy of the reactant starts out higher, and the energy of the products ends up lower, indicating an overall decrease in energy during the reaction. When the energy is released during a reaction, delta H is negative, and the reaction is considered exothermic.